Can you guys all see the screen? Great. So, just a quick review of last session. Does anyone remember what models we were using and what we learned the last time? You can just type in the chat or unmute yourselves. Yep, so Avinaya, sorry if I'm mispronouncing your name, you can correct me. And Kavya wrote linear and logistic regression, so that's great. I'm glad that you guys remember that. So the linear regression is on the left and then the logistic regression is on the right. And so some of the advantages for logistic regression that we found out last time is that it's bounded. So we usually use it on categorical data when we're classifying it into two classes. So we can denote that with 0 and 1s. So today we'll be learning something a little different. And so today we'll be first learning about decision trees. So decision trees are similar to a flowchart, which is like the easiest way to put it. And the correct definition is that the decision trees are a predictive model that uses binary rules, and they're comprised of leaves and nodes. So if we look on the diagram, we can see that there are the root nodes, which are at the end, and that is all of our data. So if we look at the stuff that we did last time, for the heart disease prediction, we could call our data as the root node. And then we could determine that our internal nodes are like different features. And at each feature, we want to split our data into different leaf nodes. And the internal nodes are where the splitting happens, and the leaf nodes are the terminal nodes. So it's called a decision tree because when we visualize our model, so say if we have a lot of data, it'll end up looking like a large tree because there's so many splits, and then like these splits are like, they're similar to tree branches. And that's why like the terms used in decision trees, it sounds like we're talking about leaves and stuff like that. So it's just similar to a tree. And the internal node is similar to a test attribute. So an example of this is like whether a coin flip comes out to be heads or tails. So we could denote like heads on the left and then tails on the right. And then this is how we would use to classify things into different classes. So our leaf nodes would be the prediction of the class. So if you remember last time we were doing the heart disease prediction, the leaf nodes would either say it is a heart disease or there isn't a heart disease. And the paths from the leaf or the root to the leaves represent classification rules. So if this was like, say the person's age, or like for the heart disease prediction, like BMI, if this was like really, if the person had a high BMI, we could put a threshold at this node. And if the person is higher than the threshold, then the node would split and say this person has, oh shoot, I forgot to start recording. Oh wait, I think someone started. Okay, thank you. I got so scared again. Okay, thanks, sorry. So what we do with decision trees is that they're nice that we can actually model nonlinear data. So if you remember in our like linear regression, we were talking about how usually we need like linear data to use the linear regression, or we can use like polynomial regression, but then we'll run into problems such as like overfitting and stuff like that. So decision trees can be used to calculate probability of getting a category or classifying to a category by assigning the data to the most likely class. So like I was talking about for the heart disease prediction, the leaf nodes would tell us the probability of being either getting a heart disease or not. And our decision trees are made up similar to like an if-then, so like a hypothesis statement. So like if this person's blood pressure is greater than this, then a value, then they will have heart disease, or they'll be more probable to get a heart disease. So We use tree generators to make our decision trees, and the tree generator determines what variables to split our nodes at, and the decision to either stop or keep splitting at a node, and assigning terminal nodes to a classification. So if we look on the diagram on the right, we're trying to predict whether we should walk or take the bus somewhere. So so here we have all of our data, and we're splitting it by the weather. So if it's sunny, then we'll look at the time, and then if it's cloudy, we'll determine whether or not we're hungry. And if it's rainy, then we'll automatically take the bus. So these are similar to like flow charts. And we see here there's like these would be like the features in our data. So if you remember in our heart disease prediction, there was like female gender and like BMI and age and stuff like that. So we could make each of our internal nodes or our root node a feature, and then we would use these to split on our data. So here we see we have like a threshold. So if the route is great, or if it's over 30 minutes, then, or if it's less than 30 minutes, we should take the bus. And if it's greater than 30 minutes, we should walk. And here we have a threshold, but here we have a binary classification. So if we're hungry, then we should walk. And if we're not, then we should take the bus. So now it's your turn to create a decision tree. So we're gonna take like 5 to 10 minutes, and you guys can come up with your own topic to create a decision tree, and then we can share ours together. And if you have any questions, you can like ask right now or type it in the chat, and we can go over how to create a decision tree. You guys can choose any topic, and if you would like, you can go back to our logistic regression and look at the heart disease prediction, and then you can make a decision tree for that. Oh, also, as you guys are working on the decision tree, once you're done, you can like write done in the chat so then we get like a good fe- a good feel of where everyone's at and when we should move on. Okay, great. So I think people are finishing up now. So if you guys want to share, you guys can like type in the chat what you created, or you can unmute and talk about your decision tree. Or else I can go first. So I created a decision tree about headaches because usually some days I wake up and I have like a throbbing headache. So and Kavya asked, we can have multiple internal nodes, right? And yes, you can. You should. Like, if we have a large data set in machine learning, we're going to have a lot of internal nodes and like branching and stuff like that. So for my example, my first split is at the question, did I get over like 6 hours of sleep? And if the answer is yes, then the probability of me getting a headache is like less than 50%. And if it's no, then we go to the next node, which is like, did you drink coffee? Because usually if I drink coffee, I feel like I have a more probable headache occurrence. And I just created my decision tree with like stuff that affects my headache occurrences. So if anyone else wants to share, you can like type in the chat or you can unmute. So I saw in the chat that Abi and Josh and Kavya finished. So if you guys would like to share, um, feel free to type in the chat or unmute. Oh, so Kavya wrote in the chat, for investors out there, I would create a decision tree that can help decide whether or not to buy a certain stock. Some of the internal nodes would be to include whether the company met its earnings, whether its average change in stock price is positive or negative, and what the stock's rating is. For the stock's rating, there would be a threshold value. So that's great. And there is a lot of like machine learning models out there that are used to predict stock price and like the stock price movement. So that's a great application of decision tree. And thank you for sharing. Um, if anyone else wants to go, you can type in the chat or we can move on to the next part. Oh, and Abi said, mine was about whether a college should admit a student based on in-state, out-of-state, GPA, etc. Yeah, that's great. I know like a lot of topics there are criteria for, so we could make a decision tree for like almost anything. And that's a great applicable way to use a decision tree. So thank you everyone for sharing, and we'll move on to the next topic, which is ensemble models. And this is to segue from the decision tree into the next model that we'll learn. So ensemble models combine results from different models, and ensemble models generally perform better than an individual model. So if we look at the diagram on the left, we have like individual decision tree models, and together they create an ensemble model. And this ensemble model is what is called the random forest. And we'll be exploring that later in our code and also later in the lecture. So ensemble models work as like a divide and conquer method. And decision tree learners individually are kind of weak as a model, but together they create a really strong model. So if we look at the diagram on the right, we see that the gray lines represent like a weak learner model. And then together they create the red line. And we can see that the red line generally like fits our data better than any single gray line model. So this is just to show that ensemble models generally perform better than an individual one of their like constituents. And basically, the random forest model is an ensemble of decision trees because like forests are created of trees, so like the name is kind of intuitive, and each tree makes a class prediction, and the class with the most votes is the model's prediction. So this tree, so the data is passed into a lot of trees, and then each tree makes a decision, and then each decision plays a role in the final decision of the rainforest classification. So the rainforest model is an ensemble of decision trees, and the random forest model is a large number of relatively uncorrelated trees. And the most important part is that these trees have to be uncorrelated. If they're correlated, then it's basically having similar models, and that won't help us. Because if you remember last time we were talking about error and stuff, and like over predicting and under predicting. Oh, so someone has a question. I can answer that first. So, um, Go asked, how do machine learning models work for apps like Google Maps? How is it able to use those models to give you suggestions on where to go based on where you usually go? For example, when you leave to go to work at 7 in the morning, Google Maps suggests that you go to work because that is where you usually go. So I'm not sure. That's a great question. And those are recommender systems, so sometimes there might be AI used in like machine learning, but my guess is that machine learning isn't really necessary for that. They can just have like a database storing that, and I think Krish can give like a more detailed explanation. So Krish, if you want to like unmute.
Yeah, so Google Maps usually uses things like RNNs and recommender systems to build those kind of things. So what it essentially does is it takes previous data and it kind of makes like a certain a tree makes an idea build an understanding of previous data and previous interactions with the user. And based on those interactions, it creates like a recommended system. And that's a recommender system is.
Yeah.
So like in this session, we're not going to go in detail on that. We're just covering random forest and decision trees. But yeah, those are basically just recommender systems.
Yep. And if you wanted to learn more about recurrent neural networks, we'll dive into that, I think, in our last session. So, yeah, we will be working with recurrent neural networks for session 8. Um, so the key, like I was saying, for the random forest classifier, it's an ensemble of decision trees, and the important part is that the trees are uncorrelated. So like our linear regression model, we have some trees that overpredict and underpredict our data. And the random forest is kind of like an average. So if we go back to the last slide, like the red line is kind of an average. So if we have similar trees, then some of the trees would basically just be all over the place, and we really want the middle, like the average, which is why we need uncorrelated trees. And the collection of trees protects each one from their individual errors. So like the bottom gray line, that's like severely under predicting the data, and then the top gray line is severely like over predicting the data. So the like collection of the models would be the red line, and that's like a better fit for our data. And so how do random forest works? So um, the data is a randomly selected subset of our total data set, and that is used to determine whether we should split or continue a node. And then the different a different subset of the training data is used to train each tree, which that's how we create the uncorrelated trees. If we use like the same data every time, then there's a higher probability that we get correlated trees. And random training data is used to estimate error and variable importance. So a key feature of the random forest is that it can determine which features are important for predicting the model. So last time we were talking about overfitting with our polynomial regression, and this time we'll talk about overfitting when we have like too many features. If we have too many splits in our data, then our model won't be able to generalize on new data that it hasn't seen. And the classification is made by the number of outputs from all the tree, which means that it's like a weighted average of all of the classifications from all the decision trees. So how do we split the data for the random forest? We use a method called bootstrapping or bagging. So decision trees are really sensitive to the data that they are trained on, and small changes in the data set can result in very different decision trees within the ensemble model. So random forest models take advantage of this by sampling the data with replacement. And the important part is the replacement. So if we have our original data, we have like a multi-class classification problem. So we want to maybe this would be like predicting what animal it is. So blue could be cat, green could be dog, and then orange could be like horse, and then yellow could be like rabbit or something. And what we want to do is we select our data with replacement. So we see that like all of these, we for our sampling methods we want 9 pieces of data like our original data, but this time for the data for each tree we're like selecting it with replacement. So although we've already picked, this one is like our original data, and then if we look at this one, we have this is like the same data as before, but it's just rearranged. And then if we look at the last one, we have now 5 cat classes. And how we do that is we sample with replacement. So even though we've chosen 3 blue already here, we can still select more blue because when we're sampling, we add like whatever sample that we took out back into our data. And that's how we create a large combination of data for each tree. And oh, whoops. So I guess I accidentally skipped ahead. So are random forests used for classification or regression? And the answer is both. And Kavya said, can you please go to the previous slide? Yes. So if you have any questions, you can like type in the chat. And I guess so the main point of this slide is to show that if we have a sample size n, so in this case n is 9, we have like 9 samples, we're still going to feed each tree with 9 samples. It's just that the samples that we feed into each tree can be different because we're selecting our data with replacement. And if you guys have any questions, you can type it in the chat and we'll answer it right away. Or else I can move on. So I answered this question. So it's for both, but more commonly it's, and Avi said, when you say with replacement, where is that coming from? So if we do like sampling, let me go back to that slide. So if we have like a sample, like say in our bag we have 5 balls, three of the balls are like blue, the other 2 balls are white. So if we choose a ball from the bag, we could choose like a blue ball first. That would mean there's 2 blue balls left and 2 white balls left. And then if we were to pick another one, with replacement means we're adding another blue ball back inside the bag, and then we're choosing again. And then without replacement means that we have 4 balls left and we're choosing 1 out of the 4. But with replacement means we're replacing the blue ball that we already chose, and then we're picking again. So we can think of our data kind of like, Navi said the same, asked, so when we're replacing it, the same you took out or a completely different one. So for our data, we would be picking the same that we took out. But usually when our data sets are so large, it's really improbable that you're going to get the same data again. So in like the analogy with the bag, we can think of our original data as like a bag containing our original data, and then when we're picking like a ball out of the bag, we're like selecting which sample or what data we're going to be using. And why is bagging necessary? That's a really good question. So we need to use bagging so that our trees are uncorrelated. So let's say we just feed in the data for so let's say we have like our random forest model has 3 decision trees. So bootstrap sample 1 would be the data that's fed into decision tree 1. Bootstrap sample 2 would be the data that's fed into decision tree 2, and then so forth. So if we fed the decision trees with the same exact data, it's very probable that they're going to get the same results. But we want our trees to be uncorrelated, remember? So if we go back to here, we want some of the decision trees to like overpredict and some of them to underpredict, so that when we average them to create our ensemble model, we'll get like the model that best fits our data. So in the same way that we want some nuances in our model, and that's how we know that the models are uncorrelated, because they have like different results. But if we fed the same data into each decision tree, it's very probable that all the trees are the same or very similar as the result. So when we feed in like different data, like say if we look at like bootstrap sample 3, it's very different from bootstrap sample 1 and 2, because there's like no samples of green and there's 5 samples of blue. So the tree that comes out of bootstrap sample 3 is going to be very different than the bootstrap sample than the decision tree that comes from the bootstrap sample 1 data. And that's good, so that when we create the ensemble, which is like all the models combined, we'll have like a very sophisticated model that can learn like nuances in the data from the variance in between the models. Hopefully that made sense. And if it didn't, you can just like type in the chat and I can like try to explain it again. But hopefully that answered your question. So random forests are used for both classification and regression, but usually it's used for classification tasks just because it's more prevalent, and the random forest is really powerful for classification tasks. So does anyone remember what the difference between classification and regression are? We talked about it in the last session, so if you guys want to like type in the chat what the difference is and maybe some examples of classification versus regression tasks, that would be great. Okay, I'll just answer it because I want to be able to finish this all before so that we can have time to go to the coding section. Oh, Kavya said classification is labeling an object slash piece of data, and regression is used for predicting continuous values. So that's great. That's actually perfect. I would word it the same way. So thank you for answering. And now we want to determine how our random forest model has good splits or nodes. So this is similar to our um, error from last time, so our loss function, and we want to determine whether our model is going to predict well. Sometimes if we have too many splits in nodes, we'll end up with like a overfitting model, and the model won't generalize to new data, which is really bad because our models should be able to generalize to new data. And so first we're going to be talking about the Gini impurity. So the Gini impurity tells the probability of misclassifying an observation. So the impurity measure is on the y-axis, while the probability is on the x-axis. So for random forest, we want a lower Gini number because that means our split is better and we have a lower likelihood of misclassification. So the misclassification, that means like if we go back to our heart disease prediction, the misclassification is if we say like this person's going to get a heart disease when they're actually not. So we're putting the wrong label for the data. And the next measure of our random forest is entropy, which is the measure of randomness, or like just yeah, I would say randomness. And there is a mathematical formula for entropy, but it's a little too technical and nitty gritty for this class. So but if you're interested, you can look it up, and it's kind of like complicated, but the good models for machine learning, they want to reduce entropy, which is to reduce uncertainty and reduce randomness. So if our models have less randomness and uncertainty, then we have a better model. And to measure how well our random forest is doing, we can use information gain, which is subtracting the entropy. Oh, and Kavya asked, why does it say entropy equals 1 in the previous slide? So if we go back to the previous slide. Oh, so here we have class A has 5 and then class B equals 5. So entropy is just a measure of randomness and uncertainty. So my guess is that because it's like split evenly, then the entropy would be 1. And then, so for the first one, we see that class A is 0 and class B equals 10. So like the entropy is 0, and that would mean like a really low measure of randomness because all of the data is in one class. So like you'll only be predicting like B and stuff. So information gain, we calculate that by subtracting the entropy of the weighted entropy after a split from the entropy before the split, and that will tell us the information gain. And the greater reduction in uncertainty, which means the more information gain we get, the better our model is predicting. So we want more information gain, and to do that, we want to choose features to split and create our nodes at for higher predictiveness, which leads to a higher accuracy and also less purity and lower entropy. So what we're aiming for is to reduce the Gini impurity value and also lower our entropy. And the sklearn library, which we're going to be using like last time, they do all of this stuff for us, so we don't actually have to do the math out, but it's nice to learn and to know what's actually happening like behind the scenes. And this leads us to the question, how many nodes do we actually need? And this question is really hard to answer because generally we want enough nodes so that our model can learn the representation of our data, but we also want to be caution about like overfitting and stuff like that, because we see when we have like a depth, which means like how like tall our tree is. If we have like a lot of nodes, then we can say the depth of our tree is large. So this one would be a depth of 5, this one's 4, 3, and then going all the way down to 1. And if we have a depth of 1, we actually can't even like classify it pretty well. We only have like 2 classes, but we're trying to classify 4 classes. So we'll actually be experimenting on this data in our notebooks today. So we see that for this data, I would say like the depth of 4 is pretty good, or 5. We just want to be aware of overfitting, because if we have too many, then if our depth is too large, then the model can't predict well on newly seen data. So hyperparameters. Does anyone remember what hyperparameters are? We were using them for the logistic regression and linear regression model, but it's okay if you don't remember. And these are examples of the hyperparameters for the random forest model. I guess I'll just answer the question. Or Avi said it's used to control how it learns. Yeah, that's perfect. So these are the variables that we can adjust to obtain a model with optimal performance. So today for our random forest model, we'll look at max depth, which is the maximum depth of our trees. And this is important because this talks about like the depth in here. So if we wanted a depth of 1, we would specify it using this hyperparameter. And then we also have min sample split, which is the minimum number of samples required to split at a node. So this is kind of this is to prevent overfitting. Like sometimes we want to specify, we don't want like the tree to create a new node just because one piece of data is like has like a deviance from like the normal, because then we'll like severely overfit and our model won't be able to predict on new data. And then we also have the min impurity decrease, which is the threshold for impurity decrease to have a split. And the impurity is the Gini impurity that we were talking about before. And now we'll be talking about feature selection and feature engineering. And this is how we make our model perform better. So say we run a random forest model on our data and we're getting pretty low accuracies. There are certain like steps that we can take to make our model predict better. So using all the features in our data sometimes does not get the best results. So we want to use more informative features, but less number of features to make a prediction. So if we pretend like the diagram on the right is our data, we have features on the top. So these features could be for like, if we talk about our heart disease prediction from last time, this could be like your age, this one could be your gender, and this one could be your like BMI and stuff like that. So not all of these would be informative for our prediction. So if we eliminate certain features that are uninformative to our prediction, we usually can get better results. And also, so say like this feature isn't important and this one isn't important and these three aren't important, we can eliminate them and we can use this feature, and this feature to make our predictions. And not only is it more computationally feasible for the computer because we're just working with less data, which means less computations, we can also get rid of features that don't positively contribute to our prediction. And we can also get rid of repetitive data. So our model is less likely to overfit just because it doesn't have as much data to learn. And there are a lot of methods for feature selection, but today we'll just be focusing on 3. So the important part of the random forest model is that it actually has a feature importance attribute, and we'll be exploring this with the Titanic survivor data set that we can use from Google. And then we'll also be using principal component analysis, which it basically compresses our data into a smaller form, and our computer or our machines will be able to learn a smaller representation of our data. And lastly, we have recursive feature elimination. And by the name, we'll be basically looking at our model, and each time we train the model, we'll eliminate the feature with the least importance. And then we'll keep on eliminating features until we have like the top n features. And this n you can specify. Yeah, and most of the times when you're actually doing feature engineering, you'll like play around with it and change the number of features that you want to like 5, 10, all the way to the maximum number or the maximum number of features in your data. So the first method of feature selection is the random forest feature importance attribute. So I made an acronym for it, RFFI, and the random forest provides a feature importance attribute that weighs the features in the data set accordingly. So if we look at this data set, we see that like this feature is the highest importance, and we see that it's like 0.42 around. That's the importance. So basically 42% of the classification prediction comes from this certain feature. And then we can like put a threshold. So say we want like at least 5%. So our features have to have at least a 5% importance. And then we can have a threshold and cut it off. So if we set it at 5%, then we'd only use these 4 features for our classification, or we can either select the top n features to train our classifier. So if we do like the top 5 features, then we could just cut it off here. And I'm getting some questions in the chat, so I'd like to answer them. Kavya said, how does RFFI know whether a feature is important or not? That's a great question. So the answer is that they'll use like the Gini impurity and the entropy decrease, and more importantly, the information gain. So running the computations that from like the previous slide about like how we would determine whether our model is performing well, we can use those, and the sklearn library will do that by itself, so we don't actually have to code anything for that. Hopefully that answered your question. And then Go asked, how does it calculate this feature though? Which one is important? So yeah, these Kavya and Goat's questions were pretty similar. So it will use these 2 methods and the information gain to determine whether each feature is important or not. So the next type of feature selection is PCA, or principal component analysis. And what it does is it reduces the dimensionality of the data to store the most important information. So if we have like our original data would be on the right, so we want to reduce the 3D data to 2D data. So we can see that it's like encompassing a volumetric shape, but we don't want that. And we'll want to compress the data so that it's stored in like a sheet of paper, which would be like 2D. Or if we wanted to compress 2D into 1D data, we could use like a linear regression and something like that. And again, we don't have to actually do the math for that. The sklearn library provides us with a PCA function that we can use if we wanted to compress our data and lower the dimensionality. And this is good because our model will have to learn the most important data and the most discriminative information in our data, and it will just forget about the uninformative data, which is good because the uninformative data wouldn't help our prediction. And also this is good for the computation speed just because we're working with less data. And then the last feature selection method that we'll be looking in this class is the recursive feature elimination. So what we do is train the model, and then each time we just eliminate the feature with the lowest importance using like the information gain. And then we repeat this until we have the top n features left. And we specify what the n value is. Sometimes, like in this case, it is the number of features is 18. So what we want to do is eliminate features until we have the top 18 features. And usually if we create a graph of how many features and say the score could be our accuracy of the classification, we see that with 18 features, with the top informative 18 features, then we get the best classification accuracy. And if we plot one of these, we can just use the model with the highest classification accuracy for our data. And go ask which of these feature selection / elimination methods are most efficient. So that's a great question. If we go back, so if you're talking about efficient, I would say like RFFI and PCA are most efficient. And if you're talking efficient as in like computation, then these would be the two most efficient, because like the RFE, we have to keep on retraining our model. Each time we eliminate one feature, we retrain our model again. So if the retraining process takes like a while, then it can be too much computation for our computer. But sometimes the RFE, because we have to train our model again and again, we can get better results with that. So there is a trade-off between computation and accuracy in like a lot of machine learning, not just like feature selection. But this is a really good question for all machine learning researchers. And Goat said sort of like different computational sorting methods. So yeah, that's a great point and a great analogy. So yeah. And for like RFFI and PCA, we don't have to retrain our model. We can just automatically do it. So if we did like RFFI, we could just set a threshold and then we would only train on like the certain features that we wanted to do. We wouldn't have to retrain every time. And same with PCA. We could just compress all of our data at once. So the pros and cons of the random forest. The advantages are that it's powerful and it's highly accurate. This is one of like a very powerful and widely used machine learning model that I've seen, and it's really good at classification and regression tasks, and it can handle both numerical and categorical data, like we showed in the beginning with like the weather decision tree, where we also had like thresholds as well as yes and no for our classifications and splitting among nodes. And it runs trees in parallel, so the performance is not affected or slowed. And this is really good for computation speed. And then the disadvantages is that it's not good for high dimensions of data, such as text classifications. So in text classification, like each word could be a different class. So, and then we have like a really high number of classes, and that's not good because then we'll have a lot of like leaf nodes and stuff like that, and our tree will be very wide and it might be prone to overfitting. And another disadvantage is that it's less interpretable as an ensemble model than a single tree. So yeah, because it's, oh sorry, was someone talking? I think I heard someone, but it might have just been me. Okay, maybe it was just me. So the disadvantage is that it's an ensemble model, but this can also be an advantage because, like I said before, an ensemble model generally predicts better than a single tree. And then another disadvantage is that training a large number of trees takes a lot of memory, and that's why we'll be using Google Colab because not only is it accessible to everyone, we just won't be using memory of our computers. So now we'll explore the code. So today we'll be using the blob dataset and exploring overfitting. So when we create our decision trees, like how many splits that we want and the maximum number of depth. And then we'll also be using the handwritten digit recognition dataset, and we'll be using the random forest model to actually predict what or classify images of handwritten digits into what digit it is. And also we'll be using the Titanic survivor dataset. So if you go onto our Google Drive, and if you don't have the link to the Google Drive, I can send it in the chat. So if you go on the Google Drive, we'll be using the day 3 materials, the session 3 materials. It should be there. And it's called the Student Random Forest Model Notebook. And what I'll go over the first part together, and then I'll show you what you have to fill in to actually get yours to working. So the first part is we import our library. So this is very similar to the stuff that we did for logistic regression, just because we're using the same libraries as before. So the NumPy library, Pandas library, and sklearn. So as a reminder, to run the cell, we can click like Command A or Control or Command Enter and Control Enter, whether you're on like a Windows or an Apple product. And then if you can also, there should be like a bar at the top that says run, or you can click this like arrow and it will run. It's just usually it's easier to use your keyboard, so I will use Command or Control A. Or Command or Control Enter, sorry. So this one, we're actually creating the blobs. So if we run the cell, it will show us a visual of the 4 blobs, and we're trying to classify each data point into a blob. And these blobs are colored so you can see like what it is. And right here, we're importing the decision tree classifier, which we'll be using first. So when we run the cell, and also you'll know that the cell runs when like a number in brackets shows up, and that just tells us that our cell has finished running. And this one is the function that's used to actually visualize our model. And this one won't have an output when you run it, but if we run this, this will visualize our decision tree classifier. So we can see there's like certain splits that are happening, and each, like the area will represent whichever class it is in. And then we also have the bagged tree decision classifier approach. So this is like the bootstrapping for the data, and these are our hyperparameters. So if we run this cell, we're using the bagged tree decision classifier instead of the normal decision tree classifier. And you can see that we get a little different results. And this one is like more, you can see there's like more splits happening, and that's why the model seems to be doing better on the blob data set. And lastly, we'll have the random forest classifier, which is the ensemble model. So when we run this, we get even more like specific splits. And what you'll need to know is this line is very important to filling in the code for the next part. So you can like explore this part that I just went over, and then we'll get to the classifying digits, which you guys can do on your own. So you should be able to run the cell, and then here is where you actually have to create your model. So it's very similar to what we wrote here, except we'll be changing the number of estimators, and it says use 1,000 in the comments. So just follow along the comments, and I'll show you like where you have to write the code. So you have to write the code here and here. So when we're reading the data, it's similar to how we did it for the logistic regression. So you can also go back to session 2's notebook and look at how we did it there, and then creating the model again. So yeah, it's very similar to what we have here. And now I'll just stop screen sharing unless anyone has questions, and you guys can start working on it yourselves. And I think we can go over it towards 4:15 or in 15 minutes ish. Okay, great. I think some people are done, and if you're not done, that's fine. You can run it on your own, but I'd like to go over it now. And also, Kavya asked a great question in the chat, which was how like what is the random state hyperparameter? And this is where I wanted to bring up documentation. So the scikit-learn library is what we're using for like the machine learning models. And what's great about this library is that it provides a really thorough documentation guide. So if we look at our random forest classifier, which is what we're using, we can just search up like sklearn random forest classifier, and it'll come up with all of our hyperparameters that we were talking about. And if we scroll down to like random forest or random state, or I'll just state, state, it will say that it'll tell us the default value and also what it means. So it controls both the randomness of the bootstrapping of the samples used when building the trees, and the sampling of the features to consider when looking for the best split at each node. So if you are ever stuck and you're wondering what stuff means, you can just look at the documentation, and it's just like one Google search away. So yeah. Also, now we'll go to the answers. I'll be releasing these. I'll put it in the folder in a bit after the class. So let me just clear out output. So we've run these before, but I think I have to run the import statement again. And I'll just run this and this and this just so that I don't get any errors. And okay, so now we'll start at the here. So classifying digits with random forest. So if we run this cell, we should be able to see the digits show up. So what it's doing is it's creating a graphic, and we're using the matplotlib library to do that. So this just tells us the subplots means we're having like multiple plots, and we can see like this isn't very clear. Like some of them you can tell that this is 0 and this is like 1, but some of the other ones might be harder. Like these two are 9. So these are kind of like pixelated images, and when we talk about like deep learning, I think in the next section we'll be able to use like computer vision applications and be able to classify images like in a lot nicer way. But right now, for simplicity, we're just going to be using these images. So it's okay if we don't get like a really high accuracy. And next, we're going to be using the train test split. So the random forest classifier also has a random state hyperparameter, but so does the train test split. So if you were wondering what this meant, then you could search up train test split and random state and look at the documentation. So this was the answer, and all you had to do was copy and paste, I think, this line. And this one has random state equals 0, and you could delete that part or keep it. It doesn't really matter. So if we run this, this is the line where we're actually training our model. So model dash fit, and then we pass in the data that we want to train on. So which would be the X train, and then the labels for the data would be Y train. And then when we're trying to predict our predict using our model, we only pass in our X variables, and then we get prediction labels, and then we want to compare these prediction labels to our testing labels. And this is what the classification report does. It will compare the predictions from our model and the real testing labels, and then it'll return different values such as precision, recall, F1 score, and then average scores and stuff like that. So if you remember from last time what precision and recall means, that's great. If not, you can just look it up. And also for there's different accuracy scores. So you might see there's like macro average and weighted average. So weighted average means that you're actually looking at how many samples each class has. So if you remember from our heart disease prediction data, there was a lot more like no heart disease data instances than heart disease instances. So for the weighted average classification accuracy, it takes into account how many samples we have per class, while the macro average doesn't take into account like how many samples are in each class. And in this case, I'm guessing that the data is pretty even for each class because we get like the same results for macro and weighted. But in some instances in machine learning, you'll see that macro average scores are way higher or weighted average scores are way higher. So it just depends on the situation. And then here we're actually getting the data online and downloading it. And we see that the name of the data is train.csv. So we want to copy and paste that into here. And then we're using the pandas library, which is the PD, and then we're reading the CSV file. And when we run this, we should load the data, and then the data is called df underscore train. So if we do dot head, and the 5 parameter tells us like how many instances of the data you want to see. So we pass in 5, so it should show us the first 5 instances of the data. And we see like some of the variables in our data set are the passenger ID and the survive, like whether or not they survive. So this would be binary, where no would be 0 and then 1 would be yes. And then P class could be like what class they were on for the Titanic, and their name and stuff like that. So these are the features that will actually make nodes and splits at. And here we want to change the categorical data, so like male and female and stuff. We want to change that into numerical data, so we could use like zeros and ones. And if it's multi-class, then we could use like 1 to n, however many classes we have. So if we do that, we can change all of the data into numbers, which we have here. And we see that like the names are all unique, so every person's name is different. And now we're going to be training the model again, or calling the model and creating the model, and this is similar to the first one. And you can add random state or you don't have to. And now we're trying to prepare our data. So what we're trying to predict is whether or not a person survived or not. So we want to use the survived a feature, which is this one. So what we're calling here is we're actually indexing. So if you remember in the first class, we went about like NumPy and how we index. So we index in Panda by selecting this whole column. And also, if you have questions, you can put it in the chat. And Abi said, what's the objective of the Titanic one? So this is just to explore feature selection. I know we didn't actually predict anything, but you could use it to predict. I just wasn't sure if we'd have enough time, and it looks like we are running a little bit out of time. So this one, so if we run this, we want to drop the features that aren't important. So in this case, we dropped the survive because that's actually what we're classifying on, and then passenger ID and name, and then ticket, because these aren't really informative features. Like the passenger ID shouldn't like play a role in whether or not someone survived if the data is all random. And now we'll look at the data importance. So if we look at this, it will tell us which features are the most important. So, and I think the question on the student notebook asks like what features are the most important, and we see that like the number in front of it shows us how important each feature is. So like the gender and sex of the passenger has is the most discriminative feature of all of our data, and then the next would be age and fair and stuff. And if we wanted to use this data to classify whether or not someone actually survived, we could have a threshold, or we could do like the top n features. We could try with top 5, top 10, and then we could also try recursive feature elimination. So yeah, if you guys have any questions, you can put it in the chat. I'm not sure if we have time for the Kahoot today, so yeah. And in the chat, Kavi asks, why is survive being dropped? So that's a great question. So that's because we're trying to predict who survived. So if we're trying to predict that, we don't actually want the survived value in our x, because it's going to be the y. And if we had it as the x, maybe our model would be like, okay, the other features aren't important. So if we have survived here, our sorted feature importance might be that survived is like the importance would be like 100%, and everything else would be 0, and we could have like a 100% classification accuracy because it's only looking at survive. Does that kind of make sense? Is because we want our y variable or our prediction labels to be different than what we're passing in, because that would be basically saying like, let's predict whether someone has cancer or not, but we already know whether the person has cancer. So our model would most likely take advantage of that, and there wouldn't be any point of having the survived being a feature in the data. That's a great question. So thanks for asking. And if anyone else has any other questions, you can let me know. Or I think we can just end today's series with this. And this is the regular machine learning part. And then tomorrow and for the future sessions, we'll be diving into deep learning. So we'll be learning like more complex models, and I think the more complex models are a lot more interesting, in my opinion, because there's just a lot more applications that we could use deep learning for. So yeah, thank you guys for coming. I hope you guys learned something new. And